3 of our gas law review is problem number 5 on our gas laws and conservation practice sheet. And it talks about a tank of gas. So we know that's a contained system. The tank of gas contains 480 grams of oxygen and 80 grams of helium at a total pressure, so that's both gases together, of 7 atmospheres. And it wants to know a whole list of the following things. So question A says, how many moles of oxygen are in the tank? So we can do that simply. We know that we have the mass of oxygen, so we can take 480 grams of oxygen. We know that oxygen is a homonuclear diatomic element, so there's always 2 of them, and so its mass is going to be 32 grams per mole. And so we can solve that there are 15 moles of oxygen in our tank that we're looking at. So how many moles of helium are in the tank? We solve that the same way. We have 80 grams of helium. We know that the molar mass of helium is 4 grams per mole. And so that we can solve that we have 20 moles of helium in our tank. Question C says, what is the total moles in our tank? Well, we have some oxygen, we have some helium, and if we add them together, we have 35 moles of gas in our tank. Question D says, what is the mole fraction of oxygen? So our mole fraction equation, mole fraction of oxygen, is going to equal the moles of oxygen divided by the total moles. We've just solved up here that we have 15 moles of oxygen and we have 35 moles total in our tank. And so that solves that the mole fraction for oxygen is 0.4286, or oxygen takes up 42.86% of our gas in our system. The mole fraction for helium, we use the same equation, but we solve 20 moles of helium over 35 moles total, and we find out that the mole fraction for helium is going to be 0.5714. We could have also subtracted 42% from 100% and found the same number. And if we add those up together, they do give us 100%. So that's good. And then it asks us, what is the partial pressure of oxygen? So we know that we have a couple equations for that. Pressure total is going to be the pressure of the oxygen plus the pressure of helium in this system. Those are the 2 that we are given. Now we know from our mole fractions that our mole fraction for oxygen is 42.86%. So that applies to the mole volume and also to the partial pressure. So since we're given the total pressure in atmospheres, we can multiply that by 42.86%, and we can find that the partial pressure for oxygen is going to be 3 atmospheres. By the same token, the partial pressure of helium is going to be 7 atmospheres times 0.5717. No units, remember, because it is just a ratio of those. And we find that the partial pressure for helium is 4 atmospheres. So we can use our mole fractions to find our partial pressures, or we could find our partial pressures to find our mole fractions. Question number 6 says that we have a sample of helium that has a volume of 0.5 liters at STP. So we know that our temperature is 273 Kelvin. We know that our pressure is 1 atmosphere. And it wants to know what is its new volume if the temperature is increased to 52 degrees C. So we're going to add our 273 and we'll find that that is 325 Kelvin. So our temperature is going from 273 to 325 Kelvin. And it also is going to increase our pressure 1, is going to increase to 950 torr. And we know, of course, that we want that in atmospheres. So if we have 950 torr, we know that 760 torrs are in every atmosphere. So that converts to 950 1.25 atmospheres. And so what are we trying to figure out? We've identified all our variables, and we know that we have pressure, we have volume, and we have temperature. So it looks like we want to use the combined gas law. The combined gas law is P1V1 over T1 equals P2V2 over T2. We don't have any moles, so we don't need to use the Pivnert. We can use just the combined gas law, and we can substitute in all of our variables. So 1 atmosphere times 1/2 a liter divided by 273 Kelvin equals our new pressure, which was 1.25 atmospheres. We don't know what our new volume is, and we know that our new temperature is 325 Kelvin. So again, be careful with your algebra when you're doing this, and step through it carefully. So it turns out that it would be this whole thing equals 0.002, and then you'll multiply it by the 325 to get rid of it on that side, and then you will divide it by the 1.25 atmospheres to equal your volume 2. Okay, so when you're moving something from the denominator, you multiply it. Moving something from the numerator, you divide it. And we find out that our final volume is 0.47 liters. So just a little bit of change when we change the pressure and the temperature there. Please keep your units in your work, because it really does help you figure out where you're going with things and keeping them all straight. So number 7 is another mole fraction problem. It says, what is the mole fraction of each component of a gas mixture that contains radon at a pressure, so we have radon at a pressure of 2.01 atmospheres, and we have diarsenic pentoxide. So we're going to have to figure out how to write that. Diarsenic means we have 2 arsenics, and pentoxide is going to mean that we have 5 oxygens. It ends with an IDE, so we know that it's not a polyatomic ion, it's just arsenic and oxygen. Diarsenic pentoxide. And so we have that at a pressure of 1.03 atmospheres. Okay, and so we've identified what we're given. We have 2 pressures, and it wants to know the mole fraction. And so we can do our total pressure is going to equal P1 plus P2. So total pressure will be 2.01 atmospheres plus 1.03 atmospheres to equal 3.04 atmospheres. And we can figure out that our mole fraction for radon is going to equal our pressure of radon over the pressure total. Remember that mole fraction is simply a ratio, so we can use that for the number of moles or we can use it for pressure. So we have the pressure of radon is 2.01 atmospheres, and we know the total pressure of the system is 3.04 atmospheres. So we know the mole fraction of radon is going to be equal to 0.66 or 66%. By the same token, the mole fraction of diarsenic pentoxide, we can take 66% and subtract it for 100 and find that it is 34% or 0.34, or we can do the math, 1.03 atmospheres divided by the total atmospheres will give us the same answer of 0.34 atmospheres. So the mole fraction for diarsenic pentoxide is going to be 34%. Remember, mole fraction ratio tells us about the partial pressures or about the number of moles in a closed system. Question number 8 tells us that we have a sample of boron gas collected over water at 20 degrees C and a total pressure of 1 atmosphere. The volume of the gas collected is 250 liters, and it wants to know what is the mass of boron that's collected. So when we're using gas that's collected over water, we know that there's going to be some water vapor in there, so we need to know the temperature. And there was a chart. We were given that at 20 degrees C, the vapor pressure of water is going to be equal to 17.5 torr. And so what do we know? We know that the temperature, we know the pressure total, we know the volume, and we know the partial pressure of water. So we can use our partial pressure equation. So the pressure of the water plus the pressure of the boron gas is going to be equal to the total pressure of the system. So we can substitute that in. We of course want to convert torrs to atmospheres. So we know in every atmosphere there are 760 torr. And so that converts to 0.023 atmospheres. So, and that is the partial pressure of water, 0.023 atmospheres. And the pressure of boron is what we're trying to figure out. Okay, so we're not quite there yet. So we need to figure out how many moles of boron we have, and for that we can, that's not right, we have the atmosphere, we know that this is, I'm losing it, 1 atmosphere is the total pressure, and so we can solve for boron by substituting that. So the pressure of boron is going to be equal to 0.977 atmospheres. Then we can use our Pivnert to solve for the moles, because now we have pressure and volume, and we have R and T. I'm rearranging that so that you can solve for moles. And so we solve that by 0.977 atmospheres times our volume, which is 250 liters, divided by 0.0821 liter atmospheres per mole Kelvin. And our temperature which is 273 plus 20, because we want it to be in Kelvin. We do all the math there, and we find out that we have 10.15 moles of boron, and it wants to know the mass of boron, so we convert our mass to moles. 10.15 moles of boron. We look at our friend the periodic table to find out that the mass of boron is 10.8 grams per mole, and yep, I did it backwards, 10.8 grams per mole, and that's going to equal 109.6 grams of boron at that, given those conditions.